aspect. So traditional filters depends heavily on mathematical models, as we have seen just now. So as the number of states increases or the state dynamic complex dynamic systems, the mathematical modeling is obviously a complex mathematical model we need to develop. But AI based models learn directly from the data. So we need not bother about taking these equations, writing these equations and all. So that learn directly from the data, and accordingly we are going to give the better results. So we have different techniques here in the AI based approaches in signal processing. So in this one, neural networks. So neural networks is one such thing. So which actually learn patterns in data by adjusting internal weights to approximate complex nonlinear relationships in signals. And CNN is convolutional neural networks. So this is for spatial and spectral filtering. So where it is used for extracting the spatial features like images, grids, so and spectral features like frequency components and so on. So they perform filtering through learnable convolutional kernels. And RNN is another one. RNN is a recurrent neural network, and LSTM is a long short term memory. So these are for the time varying signals. These models basically capture the temporal dependencies, making them ideal for signals that change over time, like speech, sensor data, or communication signals. And deep encoders, deep auto encoders. So this is for the denoising. So these auto encoders is a neural network which is used to learn compressed representations. So deep autoencoders learn to reconstruct clean signals. So by removing the noise in the encoding and decoding process and so on. And GAN is another one. So this is generative adversarial network. So this is for generating the clean signals once again. So this uses a generator plus a discriminator to create synthetic clean signals. So that match the distribution of real clean data. So these are basically useful for denoising, signal reconstruction, data augmentation, and all. So why actually these AI models are superior to traditional filters means AI-driven models overcome the key limitations that were existing in the classical filters like Wiener filters or Kalman filters or LMS, RLS, and so on, because they can handle non-linearities. So this is one of the major thing. So they can handle non-linearities. So traditional filters assume linear models or approximate the non-linear systems in as if they are linear. But AI models learn non-linear mappings from the data itself, and also they adapt to non-stationary noise also. So if you see in the Kalman filter, so we have considered that it is a additive noise and Gaussian noise. But these AI based models adopts the non-stationary noise. So real world signals have noise that changes over time. So deep models dynamically adapt to varying parameters. And another important thing is learn directly from the raw data. So no need for handcrafted models or assumptions and so on. So directly they learn from the raw data itself, and they provide end-to-end learning. So filtering plus feature extraction happen in one integrated architecture. Okay, so neural networks can learn complex patterns even in the presence of noise. CNN learns spatial and spectral features, and RNN and LSTM learn time varying signal behavior. Okay, and auto encoders learn to denoise the signal, and GAN can generate the clean versions of the noisy signals. So this data-driven approach allows AI to overcome the limitations of classical filters, especially in non-linear, non-stationary communication environments. And AI for filtering and denoising. So AI-based filtering techniques are revolutionizing and signal processing. So deep denoising autoencoders can handle complex noise patterns that classical models cannot describe. So similarly, CNN-based filters. So they are widely used in image denoising, speech enhancement, and so on. Even in the radar signal cleanup, RF fingerprinting, and so on. And GAN-based denoising produces highly realistic clean signals and is useful in satellite communications and also in medical imaging. And AI-driven adaptive filters can update in real time without needing explicit mathematical models. So that is the ultimate thing in the AI-based adaptive filters. So no, without needing any explicit mathematical models, so we can use these models for getting the better results. So if you observe these AI in communication applications, so we have noise reduction in wireless communication systems, channel estimation, modulation recognition, spectrum sensing, beamforming, and so on. Madam, so can I continue for 10 more minutes?
Okay, madam. Okay.
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 So, yeah, so if you see one practical application, we'll analyze AI in is it visible? A enhanced noise reduction in wireless communication system. So here, in modern cellular and wireless networks, 4G, 5G, 6G received signals are often heavily corrupted by the interference and fading and ambient noise. Where AI-driven noise reduction uses uh, these machine learning or deep learning algorithms, models to clean the signal before demodulation and improving clarity as well as the reliability. So here the problem addressed is the traditional signal processing methods like Wiener filters or spectral subtractions are limited in highly non-linear or dynamic environments, right? So wireless channels in urban areas change rapidly due to mobility or multipath and interference from the devices. So here AI-driven techniques like deep neural networks or recurrent neural networks like LSTM are trained on large data sets of noise and clean signals. So the model learns complex noise patterns and predicts the clean signal from its noisy version. So even in 5G, 6G research, denoising auto encoders and transformers are increasingly used. So here, how basically it works means it collects noisy wireless signal samples first. It collects noisy wireless samples for signal samples first and pre-process that information by using FFTs or normalization or framing. So different techniques are available, and then training. So train AI model with the paired noise versus clean signals. So it trains the model with the paired with noise as well as the clean signals, and then deploy a model in the receiver for real-time denoising. And finally, send the cleared signal to demodulation or decoding blocks. So these are the different works that has been done in the AI-driven signal processing. First, collecting the noisy wireless signal samples and pre-processing the data and train AI model with paired noise as well as the clean signals, and then deploy model in the receiver and finally send the cleared data. So if you proceed with all these things, the key performance improvements are signal to noise ratio. So it leads towards a higher signal to noise ratio after denoising, and reduced bit error rate, especially in low SNR conditions. So especially in low SNR conditions, bit error rates are very high. But in AI driven systems, the reduced bit error rates, especially under low signal to noise noise ratio conditions exist, and also the quality of service, especially in voice, video calls, IoT links, and also adaptive to varying noisy environments. Okay, so these are the different things we can achieve. So here, under these circumstances, if you the performance measured at low to moderate signal to noise conditions, noise ratio conditions, from minus 5 dB to 10 dB in fading interference wireless channel. I have done it under these conditions for different filters, different signal processing techniques. So Wiener filter, Kalman filter, and also AI based approach, deep learning denoiser, CNN LSTM approach, and see under minus 5 dB where the signal to noise ratio is under very low conditions. So I'm getting good results under such circumstances. Bit error rate is 0.12 at minus 5 dB. So lower conditions. So AI based denoising obviously improves the bit error rate by 40 to 70% over traditional filters. So especially the maximum benefit occurs at the low signal to noise ratio. So where classical filters fails under such conditions. And also the signal to noise ratio improvement. So if you see the deep learning based denoiser have the output signal to noise ratio higher when compared to the other two techniques. And error vector magnitude also in denoiser, AI denoiser, it is 4.9%. So here the quality service metrics like throughput, latency, packet loss, robustness to interference, adaptability to channel variation. So there in AI-based denoising, they shows better results when compared to the traditional filters. Traditional filters. So at least 10 to 25% higher with respect to throughput, and latency is low to moderate because it depends on the model size, right? And packet loss is 30 to 50%, and robustness is high, adaptability is strong. So these are the advantages with the AI-based denoising. So the first and foremost thing is it doesn't require any explicit mathematical modeling, and it learns from the raw data itself. So, in real world use case, telecom companies use AI denoising in 5G based stations to improve uplink performance. Even in IoT, edge devices use lightweight models to filter sensor noise. Even in the satellite communication uses AI in order to suppress the atmospheric interferences. But still it has got some limitations, since it requires a large data sets for training, and computational costs must be optimized for real-time implementation, and also the model performance may degrade if channel characteristics change drastically unless retrained. So it has got some limitations also. So these are the results I have given. And these are the comparative analysis here it is for different techniques. And this is another example, even for the biomedical application, AI-based ECG arrhythmia detection application. So this is here also electrocardiogram signals are used to diagnose heart rhythm disorders such as arterial fibrillation and so on, and ventricular arrhythmias and so on. So AI-driven model automatically analyze ECE waveforms and classify abnormal patterns more accurately than traditional rule-based methods. So here also basically the signal processing steps in AI-driven signal processing for this particular application includes pre-processing, feature extraction, classification. Okay. So here the traditional ECG analysis depends heavily on manual inspection, fixed thresholds, and simple morphology-based algorithms. Whereas AI model learns a complex variation in ECG and subtle abnormalities and patient specific patterns. Okay, so based on this one, accuracy, sensitivity, and early detection improves significantly. So, AI driven signal processing enables accurate automated detection of cardiac arrhythmia using ECG signals by combining noise removal, deep feature learning, and intelligent classification. And AI improves obviously the diagnostic accuracy, and it supports wearable health monitoring and enhances outcomes in modern biomedical engineering. And if you see, these are the future directions, future directions. So the future of filtering lies in combining classical methods with the AI. So classical methods is not actually obsolete. So we'll get the better results when we fuse it with the AI, fuse it with the classical models. Hybrid AI model based filters can leverage both the theoretical guarantees and learning capabilities. We'll see the self-learning optimum filters which are designed for the 6G networks. Edge and IoT devices to run intelligent signal processing locally. And quantum techniques may enhance filtering performance at very low SNRs. So these technologies together will define the next generation communication systems. So the optimum filters like Wiener or Kalman filters or LMS, RLS. So this forms the backbone of communication receivers, and adaptive filters allow systems to adjust automatically in dynamic environments. Whereas AI-driven filtering opens the door to intelligent, flexible, and high performance signal processing, which is critical for 5G, 6G, and IoT systems. And the future communication systems will rely on the synergy of classical optimum filtering and artificial intelligence to achieve robust and efficient signal estimation. So these are the some of the references, and thank you for your kind support and patience. So if you have any doubts,
Participants, if you have any queries, please raise. The forum is open for you. You can post your queries in the chat box also.